to do, if you ask yourself a little bit. So we share something which is very common in social sciences, actually. I speak today about a topic I was interested over the whole period of COVID pandemics, the impact of households, but it's just one example of a structural heterogeneity among countries, which has a strong impact. And I would like to explain to you how you can measure this impact. And I would love to speak about more than the European countries, but I just have lack of data about other countries to carry out the approach we did here together with the group of Viola Priesemann from the Max Planck Institute for Dynamics and Self-Organizations in Göttingen. And okay, so what are structural risk factors? These are factors which somehow are country-specific and could make it difficult or easy to control a pandemic, right? And the general question is, to which extent explain the such structural risk factors? I will name a few differences in epidemic dynamics between the countries. Because all the countries tried to do a similar thing. They tried to control the pandemics, and the outcome was very different, right? And you would like to understand somehow what happens. Now, the first thing, of course, is age structure. And that's somehow the easiest thing to understand because in COVID, at least till the Delta variant, we had with an increase of 5 years in age, doubling of the mortality. So age structure becomes very important in assessing the COVID deaths. And Germany and China are somehow here on the bad end, and Nigeria and Brasilia to a certain end are much better in terms of composition. I will speak about household, and this is the heterogeneity in a certain very relevant parameter which I will explain, the ratio between the mean squared household size and the mean household size. And you see here that Eastern European countries have much larger, this moment ratio of households. And that makes them somehow, vulnerable to the epidemic dynamics in comparison to some other countries like Scandinavian ones. Workplaces definitely make also a difference. This is relatively poorly understood still. You can imagine that situations like mining industry, if you have a large share of workforce in there, have more difficulties to control spread than countries where a lot of people work in home office and can stay at home and somehow secure themselves. And then we have still, of course, a lot of social factors. This is the heterogeneity in so-called individualism versus collectivism. The Philippines are much more collective thinking, more social thinking than the European countries and the US, and that makes, of course, a little bit a certain problem when you find agreement in the population to on certain countermeasures, like mask wearing, right? So European countries didn't like masks very much, but Asian countries have a much better performance here. This is another, heterogeneity here, trust in governments. And again, you see Eastern European countries have a very poor trust into governments, and that has an impact on the pandemics. I will not much speak about that. I just want to mention here that these are also important so-called risk factors. Mobility is the last thing, which is also pretty obvious, and there's a kind of lot of research going on this pattern here, but I will not speak about that. So let me come to the question how to assess the impact of risk factors on different countries. And essentially, you can do a couple of things, and the most natural maybe, and what most people do, is just to rely on empirical statistical analysis and look for correlations between certain measures for outcome of pandemics and certain measures characterizing patterns or structural differences between countries. So that people do, but it has somehow limited use insofar that It's difficult, it doesn't gain you very much understanding why certain things turn out to be the way they are. You could go and build complex models, and best for all European countries, like agent-based model, and then you try to simulate the pandemic with the specific conditions, and you see what is causing what. The problem is there is no agent-based model for the whole of Europe, which somehow covers all the countries. For some, there are, and they are very different from country to country. So this is just because of the lack of the model approach, not feasible. And then there is theoretical analysis, which I will present a little bit, because to an old saying, there's nothing better than a good, nothing more practical than a good theory. Okay, so theory can sometimes be helpful. And then you have to, of course, to decide what you would like to compare, deaths, cases, or hospitalizations. There are a lot of possible metrics. And the problem with all of those is, except the hospitalizations maybe, you don't know the numbers, right? We have not even in Europe found an agreement to define what is a COVID death, because the definition even within a country was changed several times in Great Britain, for instance. And so usually it's if a person becomes infected with COVID and dies within 25 days, then he counts as a COVID death. But the 25 days is a little very subjective, and they changed it then to 30 days, and then to 35, and then back to 28. So you have, even in the definition of COVID deaths, no agreement about the European countries, and even not an agreement within a country. That makes a little bit a problem. And then you have, of course, the undetected deaths. Good. So what about households and why households are somehow special? What you see on the left side is the regional heterogeneity in the mean squared household size in Poland, which is quite remarkable, right? So some regions has very large household and some people have much, much less larger household. On the right side, you see a similar figure for the European countries. And the significant role of household, especially in the COVID pandemics, but actually in most respiratory disease infections, is that in a pandemics like COVID, where you had a lot of non-pharmaceutical intervention measures, they had no effect on the in-household contact structure. So whether there was a lockdown or no lockdown, you were sitting together with your people in the household and you couldn't do anything there, right? And people didn't wear masks in household, even if it was recommendation. There are some exceptions like China, where people were put out from the household when they were detected, but this was only in China happening, as far as I know. By force, actually, they were put out. And the second point is the household contacts. If you live in a larger household, in comparison with a single household, it doesn't make a difference on the out-household contacts, right? So the single household person sits alone at home in the evening, and the multi-person household people sit together with their family at home in the evening. That's essentially the difference. Now, there is a theoretical relation, and I will not show you the details here, which relates what is called the mean out-household reproduction number. That's one input. The other thing is the household size distribution. And the third thing is the household attack rate, which I will say what it is, and the prevalence from over a certain period of time, so the total number of true cases together in an equation. Or if you know three of the things, you can compute the other one. And that's essentially applied graph theory. And you have to make some assumptions on the contact structure here. And this is my list of assumptions. So likelihood to get infected from outside the household does not depend on the household size. The in-household contact rate is stationary, it doesn't depend on the size of the household. And there is a certain spreading model within a household when an infection arrives. And you need some mixture properties for the population. And the checkpoint at which you look for the prevalence is at an end of a wave. But there could be still a lot of heterogeneity. So individually, the number of people you might have infected, or really could have infected, could be largely varying, and also the timeline of the pandemic. You don't need any assumptions on the sequence and timing of non-pharmaceutical interaction. Well, having said this, I need a few words to spend about what are the different reproduction numbers. There's a long list, that is not a complete list. And for this talk, you have to understand essentially 3 reproduction numbers. One is measuring on the individual level the so-called out-household reproduction number, which is the mean number, if you are infected, the mean number of secondary cases you produce outside the household. That I call the out-household reproduction number. Then there is, this is relevant for the phase transition epidemics, the household reproduction number. So if a household gets infected as a whole, there could be several people in the household, then the question is how many people outside the household, how many other households get infected from a typical infected household. And these are all notions about an expectation, and are asymptotic notions essentially. So you need large populations to define them mathematically properly. And the in-household stuff, and here's a picture a little bit, this is measured, the spread into household is measured by the so-called secondary attack rate, where the black person here is the, you see the black person is an index case, so the infection came in from somewhere, and there are 3 further members in the household. And here they could all 3 get infected, but the blue person maybe was previously infected, but still for the secondary attack rate, you would say somehow this is the number of the fraction of those remaining people except the index case, so it's 3 here, the fraction of those remaining people who get infected. And in this specific case, it would be equal to 1. But for the COVID, it's somehow 0.2, a little bit plus minus, plus minus a few percent. And this individual here would have an household reproduction number of 3. So 2 people here really infected, but the 3rd person was already previously infected, but it would still count as into the out-household individual reproduction number. And as a whole, this household was infecting 1, 2, 3, 4 household. This household didn't get infected actually because there was previously infection, but you counted in the out-household reproduction number still. Right? So this is somehow a short overview about the different household stuffs. So what's the plan now? Once we have a theory and we have some understanding, the first thing is we would like to estimate the true prevalence after a first year of pandemic for EU. Why only the first year? Because in the second half of 2021, the vaccination was very much impacting the things, and things are more difficult to estimate and are very much overruled by the vaccination. Then compute via the theory, once you have the prevalence and the household size distribution and the attack rate, you can compute the mean out-household reproduction number. And this is actually a measure which allows you to compare how effectively the different countries approach the COVID pandemics. It's a number which combines the state effect and the realization by the individuals in the society. I use it as an index which you can make, on which base you can make a ranking of the countries. And then we can, the theoretical predicted prevalence, compute if countries would have all the same mean European out-household R. Once I have the individual country household R computed. And then I have to check, of course, all my assumptions in the things here empirically. So the first problem is estimating the true prevalence across Europe. There are several ways, and we have here a whole research project of that. But the basic simple idea, once you have a good understanding what is the so-called infection fatality rate, so if you are infected, what is the likelihood to die given the age? If you have this function, then you can use the deaths and scale them up into into cases. And this comes with a lot of statistical fine-tuning stuff here, but that's essentially what you did. Then you can validate with some external studies, like zero prevalence studies or large cohorts from which you know the true prevalence, like in in Great Britain, for instance, and see if this works well. And this is here what we, the first thing is what we did now for Poland. And you see also that Poland has a lot of so-called surplus deaths. So what we estimate here, the true number of COVID deaths, we take the maximum value of the last few years, this is the black curve. We added the official COVID deaths. This gives you the yellow line. So it's the maximum number plus the COVID deaths. And then the red line is the true number of cases, of overall deaths in the country by week, a little bit smoothed here for Poland. And the gray area are somehow candidates for COVID deaths, for undetected COVID deaths. And you see here Poland has 3 such major gray areas where you have a lot of deaths which are most likely related to COVID, but not in the official statistics appearing here. So just to give you a figure, in the end November 2020, in Poland died 17,000 people per week. The normal number is 8,000. So it was more than twice as many deaths. This was the death rate we had in the Second World War last time observed, right? In Poland at least. Good, and this is a little bit still the question which years to include, because we have influenza here and it makes a bit difference, but not a huge difference. Now, once you have done this, you can make a comparison of the different countries here. And this is somehow by end of May 2021, European countries. Look on the right picture here only, and the blue ones are the official COVID deaths, and then this excess death, which we estimated corresponds to this orange columns, and some countries like Albania or Bulgaria have a very, very large share of COVID, additional unrecognized COVID deaths, seemingly. And of course, countries like Iceland and Norway have very small numbers in things at all. Now, the death statistics, you can, of course, continue, say, this is a picture by end of 2021, when the Delta wave was essentially replaced by Omicron, and you see it already an interesting pattern here, that all the countries below the red line are former communist countries in Europe. And with the exception of one country, Estonia here, this is the group of the former Western European countries. Okay. Now, now there are several ways going from the deaths to cases, and the way we proceed here is by what we call the country EFR. This is somehow assuming that you have 100,000 infected, proportionally distributed among the age groups along the distribution of the population by age. And they look for the fraction of those who die, for the expected value. That is called the infection fatality rate for a country, the country EFR, and that is a common quantity by which you can use. And then you take the deaths and essentially divided by this country EFR, and you get an estimator for the prevalence. Now, of course, we computed confidence intervals here depending on the assumptions of this EFR, and this is essentially a large bootstrap project, and the EFRs, of course, is based on empirical data from Great Britain you have, and we used a specific type of function which has a monotonicity here to compute then the EFR. So we start with a function which depends on age, and then we define the country specific, which takes somehow the age structure of the country into account. Good, this is this function here, but I don't think that I have to spend much, and this is the outcome. So this is now the estimated prevalence by week 22 in 2021. And you see that some of the estimations have a very, very large range here. that is due to uncertainty in the infection fatality rate, especially in younger age groups. But what is still interesting here, the coloring, red countries are former communist countries. The green ones are somehow Central European, Western European countries. The blue ones are islands. No, the blue ones are the Scandinavian countries, sorry. And the yellow ones are islands. Of course, Iceland here is not very well seen. This is also yellow one, right? So this is, and you see Sweden somehow is exceptional in terms to the other Scandinavian countries. Actually, it performed much, much worse in terms of prevalence here. But maybe they have a different household structure. So let's now look for what's happening if you include now the household structure. So that is for some prevalence vectors. Now we have a range, of course, we have a confidence interval. For some prevalence vector, this is somehow the scatter plot which you would get. On the y-axis, you see the estimated prevalence. And on the axis here, you have this moment ratios, which is a right quantity to look at and comes from theory. And the blue line now, once you have computed this out-household reproduction number, I spoke before previously here, which is characteristic for each country, the blue line is the predicted prevalence, number of total cases till May 2022, if all the countries would have done the same what Europe essentially did as a mean value. Okay? And now this is just a snapshot here for a specific prevalence vector. You would like to use some more statistics. And again, what you can see here is this coloring into these four groups, Eastern European, Middle European, Scandinavian, and islands. And what you see that essentially in 40% of the variation in prevalence is due to difference in household structure. Yeah, so this is in Pearson correlation, or this is in explained variance. If you take this predicted prevalence, taking the mean European value as a regression, a nonlinear regression, of course. Good. And based on that, now you can go further and compare countries by this out-household reproduction number. But before, I would like to say a few words on this, on what the theory actually tells you. And the theory you use here, this is somehow an important, the only important formula in my talk, which I show. This is the mean household reproduction number. So if a household gets infected, how many secondary households it gets infected? And in front stands here the average out-household individual reproduction number. Then comes this moment ratio, mean squared household size divided by household size, and then comes the attack rate in the household. And this number has to be larger than 1 to get in epidemics. Otherwise, you will have no giant component in the corresponding graph structure. And yeah, and some countries have a very large ratio here, like Poland. So this moment ratio is 4.26, and in Germany it's 2.75. So Germany has much easier situation in terms of households than Poland here, driving the epidemics up. So this is what you get now if you estimate this mean out household R, which is essentially the front factor in this formula here. Right? And this is the ranking for one specific prevalence vector. And now you can make, so Luxembourg is very much in the middle here, and Iceland is somehow much better than the mean European value. So 0 is mean European value. And some other countries, Hungary, Bulgaria, Czech, are very bad. Now, of course, this is for a specific vector of estimated prevalences, and we have a range of variation here. So let's us make a statistic on the ranking of this country, and this is what you see somehow. And that is, in terms of ranking of European countries, the final, maybe the most important type of picture. So you have countries which did considerably better in terms of how many infections a typical individual generated out household to household, right? So note that everything like the quarantine rules, the contact tracing, the mask wearing goes into that number. And you see a very, very clear advantage of the Iceland groups here. There's all this yellow one. And Greece is also in this group. It's probably very much like in Iceland, actually. Now you have the Scandinavian countries, which did, again, much better than the mean European mean. But Sweden is very exceptional. So it's really doing much worse. And you see that Sweden has a very lax strategy in terms of preventing COVID-19 here in this case. For some countries where we are not very able to estimate the positioning in this ranking, especially because such a young population is there, like North Macedonia, Montenegro, or Albania. So one has to be a bit cautious when saying these countries did bad. But these three are somehow the worst, Czechia, Hungary, and Bulgaria. But the UK did also very badly in terms of out-household reproduction numbers. That means the measure to control the signs. So I need maybe still 2 minutes because we started also 5:30. Yes, I still have 5 minutes because we started 5 minutes later. And I just will tell you a little bit what kind of theory we use. So we use random graph theory, where households are now the units instead of individuals, right? So this is this red graph representing the connectivity between household. And then now why coming the squared household sizes in intuitively is the argument is the number of possibilities that you have a contact between a 3 and a 4-person household is of course 12 times larger than between a single and a single household just by the combinatorial possibilities. And this amounts, when you use now heterogeneous random graph theory, according to Bolobash, Janssen, Riordan, where you can describe this kind of structure, you can define here a so-called transfer operator for an associated branching process, and from that you can derive what is the out-household reproduction number. And in that context appears this ratio here as a mathematical result for the spectral norm of a so-called transfer operator here. Okay, I will only surely mention that you have this kind of theory. And I think this is the main message here. I would have a lot of other things still to say, but maybe one remark. Now, if you look for some other things which statistically correlate well with prevalence, like the Human Development Index and this, number of estimated true cases, you see it's strongly inversely proportional here. But now you understand also in part why, because the Human Development Index involves economic factors which determine the size of the households. And then you can do a partial correlation analysis and factor now somehow the household aspect of those correlations out, and you gain somehow understanding. And that we did, and I don't want to show a lot of this stuff here. But at the end, in the workplaces is another issue, but at the end I would like to show the slide with the conclusion. Structural risks are important for proper design of pandemic preparedness plans. You have to know where your risk lies and what you can do and what you should not do. So if you are in a country like Poland, you should start with somehow measures to mitigate the pandemic a few weeks earlier than in countries where you have very small households, right? And some other factors like workplaces might additionally boost or ruse. Then there is also very little still work mathematically done, or at least in any kind of simulation, what are institutional risks due to friction and decision delay. So for instance, even in countries like Austria, I know this from the representative of the governments, after the decision for the lockdown was made, it took 10 days just to process the legal aspects through. And 10 days, if something grows exponentially fast, is a very, very large delay, right? So, and that the politicians somehow never ever understood this properly. Good. Thank you very much. And yeah, so.
So thank you, Professor Kruger.